Hello all, we are looking at exponential functions. We're going to look at Euler's number and we're going to simplify algebraic expressions and solve equations. So in simplifying the expressions and solving equations, we're going to be applying the exponential laws, our index laws, and look at some strategies in solving equations that are going to involve solutions to a quadratic equation type structure. Okay, so let's get to it. So let's first consider the situation where we'd like to loan some money from a bank. And there's a common deal that we're going to look at about 100% interest per year. Imagine that was the condition of your bank loan. Bank's going to charge you 100% interest per year. Now, that may not sound very good, but let's consider this as a scenario. We've got our four bankers here. We've got Mr. Moneyburner. He's going to charge us one calculation of 100% interests once for the whole year, and that's the whole shebang. Then we've got this gentleman here who is going to charge us two lots of interest at 50% rate, and it's going to be twice a year, biannually. And our third banker, presidential banker, is three calculations of interest, each at 33.33%, a third. And our funny man banker here is 25% quarterly. Interesting. Let's have a look at it. So, first off, our initial banker, let's say we're going to lend $1,000. So, from that, his rate that he offers 100% interest calculation. So the interest is going to be the loan amount times the rate. So the interest will be $1,000. And so the amount of the new loan is that we owe the bank now is the original loan plus the interest. So altogether it's now $2,000. Oh yes, we would hate to have that. All right. Let's consider the next bank deal. So again, the initial loan is $1,000, and this time the rate is at 50%. And we're going to calculate the interest twice. First at 6 months, and then again at the end of the year. So the first calculation of interest gives us $500. So add that on top of our original loan, $1,500. And now at the 6 months later, we calculate interest again. And we've got a total amount owing to the bank. So this is how much we would now owe the bank if we had never made any repayments throughout the year. So in that situation, this is the way we're going to progress. Alright, so let's examine this scenario. Now the rate is at a third. So a third, keep in mind, a third is a decimal number that has an infinite number of decimal places. It's a recurring decimal, so we just approximate it as 33.33%. But we're going to express our values, as an improper fraction to have it as an exact value. So there it is, 1,000 over 3 is our dollar amount for our interest. So we add that on, and it's approximately that, 1,333.33. And then now the next time we do it, we get that as our interest amount and so on. So we add that on and it keeps going up. And the third time, okay, so this process, and we can see now we're at $2,370. So that's increased somewhat from previous scenario. Alright, let's look at one more. So this time we've got a rate of 25%, and we're going to have interest rates calculations 4 times throughout the year. So that's the first amount of interest, $250, and gives us a new loan for $1,250. And so 6 months now, we're going to calculate the interest again and add that new amount on. 1,562.50, and so on. And we do this 3 times, each at a rate of 25%. Add on the interest, and then recalculate interest, and at each point the interest is compounded, and the amount goes up. 2,441, so it's increased again. And the amounts just keep getting bigger, don't they? Well, even though you think, well, 25% interest rate, well, that seems less than 100% interest rate or 50% interest rate. But because the interest is compounded each time, it increases the amount that we owe the bank. So if we kept on examining this, the banks can think, well, I can make a lot of money out of this just by having perhaps a situation like this, a 12-month interest rate at 8.3%, which is 1 over 12. Even though if they advertise this, you might think, oh, well, that's a lot smaller interest rate than 25% or 50% or 100% interest rate. So it seems more appealing. But because it's been calculated 12 times throughout the year, that 12 times creates a compounding effect on the interest, and it's going to make overall an amount even higher. So if we keep breaking it down and have a small interest rate, this time a fortnightly interest, 1 over 26 at a rate of 3.8%. And you break it down even further. How about a daily interest rate? At each calculation is 0.27%, almost 0.3% interest, but calculated daily over the course of the whole year. So I wonder what kind of amounts they would be. Well, this one goes 2,613, 2,667, 2,714. Wow, they have just kept going bigger and bigger. But if we compare how much they've gone up from all the scenarios we've looked at first there was big jumps in amounts, but then they just seemed kind of seems to like slow down a little and increase not so much. Especially here you can see 2,667 going up to 2,714. Doesn't seem like a huge increase, does it? Well, what are we going to do to make it increase really big? I think if we just push it to its limits, if we get some real smart banker, intelligent banker, new age thinking, and he came up with the idea of the infinity bank. So he's going to charge you interest at the most smallest increment, the infinitesimally smallest increment. So let's consider the scenario of breaking it down to and look at it in a general sense. And we're going to charge an infinitely small interest, but we're going to calculate that interest at a infinitely small increment throughout the year. Sounds very theoretical, but let's see what will happen. I reckon the smart banker's going to make the most money. What do you think? Alright, so in general, if we this time we're going to say we're going to have a loan of just say $1, just to keep it simple. And the rate is 1 over n. So as n gets larger and larger, the rate goes down smaller. But it's been calculated n times. So after the first calculation, you can see we've got this as our amount bigger than our initial loan. And then the second time we calculate the interest, we've got the previous loan amount times 1 over n, the rate, and we're going to now add that on to the loan, the previous amount. And if we draw it back to the original amount, we've got our P1 is the same as our P0 times the bracket 1 plus 1 over n. And so we're going to get that bracket timesing itself twice, so it's 1 plus 1 over n all squared. So let's repeat that n times. And so we get now to the power of n being our bracket, an exponential number. Alright, so there's the general rule that calculates the amount we owe each time we compound the interest. Now for bank infinity, we're going to make n approach infinity. So let's think about the limit of this amount as n approaches infinity. So that will be the amount, the loan amount. So what do you think that might be? Well, if you thought that the cost of the bank loan now with an infinite amount of calculations of interest, that's going to blow out the amount and the cost will be infinite, then in fact infinite dollars from there, you'd actually be wrong. It's not. How is that possible? Interesting thing, huh? Well, for a dollar loan, after 1 year, even with a infinite amount of interest calculations, it's actually going to be less than $3 overall. What's going on there? Well, this brings us to a natural number that this kind of scenario will tend towards. So it's not an infinite dollars. There's actually Euler's number, approximately 2.718. This is a transcendental number, which means it has an infinite number of decimal places after it. And it essentially is, Euler's number is equivalent to this expression, where you have 1 plus 1 over n to the power, all to the power of n, and then as n becomes very, very large, then what happens is that the dollar amount is actually going to increase, and then the increase is going to slow down, and it actually peters out and plateaus and trends towards a particular value, and that value is E, 2.718. It's called Euler's number, and this behavior of trending towards the number is asymptotic behavior. So this is a very important number that models growth in a whole range of contexts, from population growth to exponential decay in looking at radioactive isotopes and many other growth type models. Alright, so E involves an exponential number. E to the power of x is usually the kind of function that we're going to be looking at. So any part where you've got exponents, or we've got a number of ways in which we can simplify exponential numbers. These are what we call our exponential laws. So the first one is, if you've got two exponential numbers of the same base multiplying, then the powers, n and m, well, they add together to give you the rule. And if the exponential numbers of the same base divide, and then the powers, m and n, well, they're going to subtract, m subtract n. So let's have a look at how we can simplify this expression of exponential numbers. And we're going to express it all as a power of 2. So that means the base number a is going to be a 2. So setting that up, first off we see that 8 is really 2 to the power of 3. And 16, this base number in the denominator, well, that really is 2 to the power of 4. So then now, in this situation, which is the next index law we're going to look at, is that whenever we've got an exponential number to the power of something else, what happens now is that the powers are going to multiply. So it'll be a 3 times 1 to give you a 3, and a 3 times 2n to give you a 6n. So we have to distribute the 3 to both terms when we multiply. Okay, so we end up with this in our numerator. In our denominator, we do the same. We distribute the 4 to the 1 and the 4 to the minus n. So now we've got the situation where here's two base numbers of 2, two exponential numbers with a base number of 2, and we're going to add the exponent. So it's a 1 minus n plus 3 plus 6n. We simplify that, and now let's do the division. So the division means with the same base number 2, we're going to subtract the powers. So it's a 4 plus 5n minus, now because we've got two parts in the exponent of the base number in the denominator, then when we subtract it, we have to put brackets around it because we're subtracting both parts. So we've got to distribute that -1 to both terms. And we're going to end up with 2 to the power of 9n. There it is. And now we've expressed this expression as a power of 2. 2 to the power of 9n. So this is in general, that's the exponential law, the index law that we had just demonstrated also in that example. Exponential number to the power of something else, then we multiply the powers. So other laws are important. Negative powers, well, that becomes a fraction with the exponential number in the denominator. 1 divide a to the n. And then fractional powers, so a to the power of a fraction, that they become roots. Okay, whatever the number is in the denominator becomes the nth root. Okay, so let's simplify this expression. 9, a to the power of 3, b to the power of -4, all to the power of a half times. And we've got 2 times this part, all to the power of -2. Alright, so first off, the all to the power of a half, well, that half is going to multiply each of the powers inside the bracket. So 9 to the power of half, a to the power of 3 halves, and b to the power of -4 halves now. We do the same with all the powers of the exponential numbers inside the bracket here. They're all going to be multiplied by the -2. So it's a half times -2 and a -2 times -2. Well, that gives you that +4 there. Alright, so now because we are multiplying, we can simplify our exponents, and now that we're multiplying, we're going to add the powers. So first the numbers can multiply. 3 times 2 is 6, and now we're going to add our powers for our same base numbers. And it simplifies down to that. And here, the a to the power of half, well, we can express that as a square root using this index law. Okay, how'd you go with that one? Let's try the next one. This time we've got a fraction divide a fraction. So first off, we can express it as a multiplication of the reciprocal. So we flip the second fraction upside down. Cancel out any common factors like so. And now we multiply the numerator. So this is a 4p to the power of 5 times -4 m to the power of -1. So the numbers multiply, and that gives you that -16. And we multiply the factors in the denominator. Now, a division of exponential numbers of the same base, well, there we go. We're going to subtract the powers. So there's a subtraction of powers there, subtraction of powers down the bottom, and on the m as well. And we simplify it. Here we go. Now, see how we've got negative powers, m to the power of -4? Well, what do we say? If you've got a negative power, then that goes down into the denominator. So they swap. We have m to the power of 4 in the denominator, and our q to the power of -8. Well, that's going to be reciprocal and flip itself up into the numerator. Very good. So we can simplify exponential numbers, and we need that skill to and extend it into solving exponential equations. So let's say here's a general function. There's an exponential function. Okay, we've got, these are our parameters. A is the base number, and there's the x up in the exponent. And we've got plus d, a unit at the end. That's the general form of an exponential equation. Now, the base number a, that could also be Euler's number, E, approximately 2.7. So let's solve an exponential equation. So first off, you've got your left-hand side and with there it's an expression of exponential numbers. So we want to simplify that down first. We're going to simplify it, the left-hand side, using our index laws. So 8, we first express the 8 and the 4 all down to the same power, all to the power of base number 2 with their appropriate powers. And we apply our index laws. Multiplying gives you an addition of powers, and division gives you a subtraction of powers. And there it is all there. You've got the adding of powers, and we've got the subtracting of the 2x at the bottom, at the end as well. And we can simplify the exponent, and we get to this situation. Now, what's important to realize is one final exponential law that's very important, and it relates to the number 1. Okay, so the last index law is any base number a to the power of 0 always gives you the value of 1. Okay, it doesn't matter what that a number is. It could be minus 5 to the power of 1, to the power of 0, and that's still going to give you 1. So here we go. We have now changing the number 1 to a 2 to the power of 0. And when you get to that situation, you can say, well, the left-hand side and the right-hand side kind of look the same. They've both got the same base number 2. And so we've got the exponent. This one is a function of x, and then on the right-hand side it's a value. So what we're going to do is, for same base numbers on both sides of the equal sign, we're going to match the exponents. We can only do that if you've got an exponential number equals an exponential number and it's the same base number. Therefore, minus 3x plus 24 has to equal to 0 on the right-hand side. And from that we can solve for x. So that is the first approach to solving exponential equations, our type 1 type equation. And we've got this type. This has got a number of terms, 1, 2, 3 to be precise. So the first thing, when we solve something like that for x, we're going to bring all the terms over to the left-hand side, make sure they're all there, and we've got it equals 0. And we want to rearrange our exponential numbers so that we've got the same base and the same exponential number that's been operated on, that's inside the bracket. So we've taken the 2 out, outside the bracket, and inside the brackets is 10 to the power of x, and there's also another 10 to the power of x. So let's replace that 10 to the power of x that's inside the bracket with just a pronumeral, and let's see what we get. So let 10 to the power of x is equal to u, and let's rewrite our equation. This is what we get. When you look at that, you say, hey, that's a quadratic equation. It's just a quadratic. And we know how to solve quadratics. We've got any quadratic equation of this form. Okay, we solve with the general quadratic formula. So that's quite nifty. We get to turn an exponential function into a quadratic equation, as long as we can identify that same common part of exponential number in the two terms, and we can perform that substitution. So there's our general quadratic formula. We substitute the numbers in, and we simplify. And in this example, it works out nicely. We've got the square root of 529, which is 26. And we have to remember we have to add and subtract that 26 to the negative 17, and we get two parts. 1/10 as one answer, or negative 2/3 as the other answer. But keep in mind, these are just answers of the quadratic equation, not the exponential equation. So we've got to relate it back to the exponential equation now. So first, the next part, what we have to do is substitute back in u is equal to 10 to the power of x for our u value here. So we've got 10 to the power of x is equal to 1/10, or 10 to the power of x is equal to negative 2/3. So let's look at the first equation first. First off, I can now relate this back to a type 1 type exponential equation, where as long as I've got the same base, I can now match the powers. So 1/10 is really 10 to the power of negative 1 with that within exponential form. So therefore, x is equal to minus 1. I match the exponents. Now let's consider this one. So this says 10 to the power of x is equal to a negative number. Does that ever happen? Can you take any number, raise it to the power of something else? Do you get a negative value out of that? Not really. Does not work. It actually cannot equal to negative. And that's an important thing. Any exponential number does not equal to a negative number. So it eliminates that possibility as a solution. Alright, let's examine one more. So first off, as you can see, I've got two exponential numbers, 2 to the power of x, but this is 2 to the power of negative x. They're not the same exponential number, so I just can't straight away do a substitution for u is equal to that straight away. It's not going to help me. It's not the same thing. So let's manipulate it. What we're going to do is multiply both sides by 2 to the x. Now I chose that because it's going to eliminate this term. 2 to the x multiplied by 2 to the power of negative x. Well, same base number, I'm going to add the exponents and I'm going to have a positive x plus negative x, which is 0. And that 2 to the power of 0 is the number 1. And what I do to the left-hand side, I also have to do the same to the right-hand side to balance the equation. So that's our first step. Multiply both sides by that same factor. And this is what we end up with. I have to remember to do it to both terms. I have to distribute the 2 to the power of x to both terms. So I got 2 to the power of 2x minus 48 times, there it is, 2 to the power of negative x times 2 to the power of x, and now I'm going to add the powers and it goes to a 1. And that's correct. Alright, so now this looks familiar. This looks like a quadratic equation that we did before. So rearrange the terms, bring them all over to the left-hand side, make it equal to 0, and now identify, hey, I've got this common exponential part, this 2 to the power of x, in both terms. So I'm going to replace that with a variable u. I'm going to let u is equal to 2 to the power of x, and that just gives me a nice quadratic equation. There it is. Hey, I can factorize that. I've got two numbers, negative 16 and 3 multiply to give negative 48, and negative 16 and 3 add to give negative 13. Well, that factorized nicely to double brackets. And there it is, I've got u is equal to 16 and u equals negative 3. Now, do you remember what we said about negative numbers? What's going to happen? Well, first off, I sub u is equal to 2 to the power of x back in, and I've got these two little exponential equations that I have to solve now. So for this one, the first one here, I have to make sure I've got the same base of 2 on the right hand side. There it is. So from that I can see that I get x is equal to 4. Now that becomes the only solution because this one here, that can't be done. That's not going to work, is it? So that equation is not part of it. And it's because it always has to be greater than 0. All exponential numbers are greater than 0. So let's think about that graphically. Here is the graph of an exponential function, some base number to the power of x, and it looks like this. First off, in the negatives, you've got a to the power of a negative number, and that is a fraction. And that's a small number, so that's why it's running very close to the 0. And it's asymptotic along the 0, and it's never going to go below y is equal to 0. So it's always greater than 0, and that's what we looked at in our equations. So it's asymptotic, and then it starts to rapidly increase. It's got exponential growth, exponential increase for positive values. It goes up very fast. And another important thing here, when x is 0, you've got the base number to the power of 0, which is the number 1. So your y-axis intercept for a simple function like this is 1. So there we have it. There's our exponential number. We looked at Euler's number, 2.7 approximately, and we looked at index laws such as base number to the power of 0 is equal to 1. And we looked at how we solved equations. And when we solved equations, we identified that an exponential number can never be less than 0, and the graph shows it as well. Right, fantastic, well done, and we'll see you next time.